Today we are going to see how to implement a multivariate Newton-Raphson algorithm in Python. We are going to start with importing all the relevant packages that we need for this algorithm. I'm going to use the library AutoGrad to find the Jacobian matrix of the function. And this is a very useful library for automatic differentiation. We can take a look at its GitHub page, which is hips/autograd in GitHub. And we can install this in Anaconda using this code, conda install, and we can also install it using pip. Right, so now once we have the AutoGrad installed in our Python installation framework, we're going to import the functions gradient and Jacobian from this library, and we're also going to use the NumPy wrapper of AutoGrad. So let's take a look at how the AutoGrad library works at first before we dive into the Newton-Raphson algorithm. So here I have defined a function which is essentially x squared into y cubed, and I have written down my input x as an array such that the x1 and x2 are indexed in the array. So if I want to evaluate this at, let's say, x equals to 5 and y equals to 3, so at first what we're going to do is we're going to create the Jacobian function using the Jacobian wrapper of the AutoGrad. So the syntax is simple, just write Jacobian and then in the parentheses write down the function, parent function, and assign it to a variable. And then we just write down Jacobian function, and this is where we want it to be evaluated, which is 5 and 3. Now once we run it, we can see that it's 270 and 675. So basically evaluating this gives us that the df dx partial derivative with respect to x is 270 and df dy is 675 when x equals to 5 and y is equals to 3. So it's pretty simple and pretty helpful to use this AutoGrad for differentiation. Alright, so I'm going to demonstrate the Newton-Raphson algorithm with a linear system of equation and then a nonlinear system of equation. So here I have a linear system which I want to solve. I have the solution at hand as well so that we can compare with our algorithm solution. And just to make things quick, I have already defined the equation as 3 individual functions, and I have also defined their Jacobian functions using the Jacobian wrapper. Alright, so here is the Newton-Raphson updating rule for the multivariate case. So this is the array or the column matrix of all the initial guess for how many variables that we might have. This one is the inverse of the Jacobian matrix, which is a square matrix, and this is the column matrix of all the functions that are evaluated at their respective guesses. And so this whole thing will give us the updated guess of our unknown variables. So let's take a look at the loop that implements this algorithm. So I'm starting with I equals to 0, this is the initial counter, and then I'm setting some error which is going to be greater than the tolerance. So this is my tolerance for this algorithm. You can increase or decrease your tolerance, that's dependent on you, your idea. And I'm going to limit the maximum number of iterations to 1000. Now since I already know that this is a system of equation in 3 variables with 3 equations, so I know that the dimension m in this case is going to be 3 since I have 3 equations. So I have set m equals to 3, and since I have 3 variables here, so I will have 3 partial derivatives, partial derivative with respect to x1, x2 and x3. So n is going to be 3. So we can see that our Jacobian is a square matrix, it's a 3 by 3 matrix in this particular example. So we start the loop with this line of code. So what np.ne does is that it takes a given relational logic and returns true or false. If you look at the documentation, it tests whether any array element along a given axis evaluates to true. And we are taking the absolute value of the error because we can also get negative errors. And it's also taking in that the number of iterations should be smaller than maximum number of iterations for the loop to continue. Alright, so at first we evaluate each function at our initial guess. So I'm giving a name, assigning a name to this variable basically, which is called function evaluate here. And then I'm creating an array whose first element is function 1 evaluated at x naught. So x naught is my initial guess, which is 1 1 1, and then function 2 at x naught and function 3 at x naught, and I'm reshaping it into a m by 1 array just to make sure that the dimensionalities of this matrix stays correct. So once I have created this matrix, now I need to create the Jacobian matrix, and to make sure that the Jacobian works fine, I'm going to create another variable called flat x naught. So since we reshaped the x naught array into a n by 1 array so that we have this particular matrix dimensionality, I'm going to create a different variable called flat x naught. This is just a flattened version, so it'll be a row of all the initial guesses. And then I'm going to pass this variable through the Jacobian function. So I'm naming the variable Jac, and it's an array containing Jacobian function 1 evaluated at this flat x naught, function 2 and 3 both evaluated at this flat x naught. And then I'm also reshaping it into an n by m array, so just to make sure that the dimensionalities stay correct. Alright, now we have the function evaluated and we also have the Jacobian, so we can go ahead and get our x new, and x new is going to be x naught minus the inverse of the Jacobian dot product with function evaluate. And now we have the x new, so we can calculate the actual error. So we just write x new minus x naught is going to be the error. Once we have the error, we can update our x naught. So x naught is now equals to x new, and within the loop I have written down some print instructions. So this will let us see how the algorithm is actually proceeding towards convergence. So I'm printing the number of iterations, printing the errors, and then I'm printing out a separator for each of these iterations. Once we are done, I'm going to update my iterations. So remember, I initially set I equals to 0. So once the first iteration is going to be done, I is now going to be set to I plus 1, which is 0 plus 1, and so on and so forth. And after the loop is done, I have these print instructions outside the loop. So it's going to print out the solution, and the solution is going to be the array x new. And I'm also going to see if each of my equations evaluate to 0 at this new array of x that we get from the algorithm. Alright, so now that we have all these things set up, let's run this algorithm. I have run the code for the functions and the Jacobians, and I'm going to run the algorithm, and we can see that it takes just 2 iterations for it to solve. These are the errors, and we can see that the errors are minimizing very quickly, and the solution is 2 minus 1 and 1. And we can also see that the equations evaluated at these solutions give the function value of 0, and we can make sure that our solutions are right, 2 minus 1 and 1. So this has been fairly simple for a linear case. Let's take a look at the nonlinear example we have here. So this is a nonlinear system of equation, and I also have the solutions at hand to make sure we can compare. So I have written down this system as 3 individual functions and 3 individual Jacobians for each functions. I have given the same function name and same Jacobian name so that we don't need to rewrite the loop for the Newton-Raphson algorithm. So what I'm going to do is just run this function, run this Jacobian, and then run the loop again. And we can see that it takes 0, 1, 2, 3, 4, 5, 6, 7, 8, and it takes a total of 9 iterations to solve this. And this is the solution, 0.83, 0.35, and minus 0.49. And each of the equations now equals to 0. And we can see 0.83, 0.035, and minus 0.49. This is exactly the solution, and each of the equations are also zeroed through this algorithm. So we can see that this is a pretty robust algorithm if we have a very well behaved real valued function, and this is very useful in economics. So let's say we are trying to do a maximum likelihood estimation of some probit or a logit model, And if we want to make sure that we understand how each step is going on inside, we can actually write our own Newton-Raphson algorithm so that we can understand how this algorithm is working, and then we can get our solution using this algorithm, which is fairly robust. So that will be all for today. I'll see you guys in the next video. Thank you.